So I'm going to start off. I'm Emery Brown. I'm also one of the faculty members in IDSS. And I'm going to talk a little bit about some of the problems, one of the problems in particular we've been working on in signal processing and spectral analysis. And so, I guess it's this guy here. So in addition to being a statistician, I'm an anesthesiologist. And one of the things that we know about anesthesia drugs is that they drive the brain to oscillate. They create these very large extracellular currents. And these oscillations, because they disrupt the normal dynamics in the brain, they're the reason that we become unconscious or we weren't able to perceive pain when we're receiving the drugs. And I just want to show you what they look like. They're not subtle at all. They're very, very strong. It's the EEG under anesthesia is the strongest signal that you'll see of anything for which the EEG is used, whether it's meditation, whether it's sleep, whether it's to track some sort of performance on a behavioral exam or something. And these are just 4 different drugs that are widely used. Propofol, sevoflurane, which is an ether. We still use ether anesthetics. And ketamine and dexmedetomidine. Well, if you look at them this way, they may not look all that different, actually. But if you look at it here, you look at their spectra are quite different. And so coming up with a way that you can estimate spectra reliably and then use it to track brain states, may even develop control systems, is something which is, very, very appealing, right? So I'm going to go through like 2 sorts of questions so that I think we should try to answer for this. And this is one of them. So this is propofol. So as you may remember, propofol was the anesthetic that unfortunately was associated with Michael Jackson's demise. And one of the things that you can see here is that when someone is receiving propofol, this is time here, and it has a very strong low frequency oscillation and a 10 hertz oscillation. That's a standard signature you'll see. Every time someone gets propofol, that's exactly what you'll see, right? And then what's interesting here is sevoflurane. So this is an intravenous drug. This is an inhaled drug. We give it to you by mask. And if you look here, they're in the same drug class. In other words, they affect the same receptors in the brain. They affect the GABA receptors. But propofol, sevoflurane looks a little bit different. You see, here's a slow oscillation, maybe a 10 hertz oscillation. Here's a slow oscillation, maybe a 10 hertz oscillation. It looks like sevoflurane has an additional oscillation, all right? Now, one of the reasons that we obsess about this is that part of our research is understanding the spectral structure. Then we work on building models that we can hope understand that. So if there's a third oscillation coming in there, that means we have to think about what in the brain could cause this third oscillation once you reach a certain state. So that's kind of the question. So the question is going to be, like, is this third oscillation really there? Okay? Or is this could this be an artifact of our analyses? Right? And so here's a second question, right? So, we get people who come in and volunteer to let us anesthetize them. So if you're not doing anything some Saturday, just come drop by, yeah. And so this is an example of one of them. We gave someone an increasing dose of propofol, increasing over about an hour and then decreasing. See, it's a tantalizing thought, isn't it? See, I'm going to get anesthetized. Oh, okay, that's cool, But look what happens. All of a sudden, the person is sitting there, right? And then, boom, something starts to occur, and then you get this extremely strong oscillation here, and then here they're getting deeper, and look how it disappears almost here as you've gotten deeper. And then as we drop the drug off, it sort of goes back the other way and then disappears again, all right? And so look, I've put white lines here. And so here the person was clearly awake. Here they were starting to lose consciousness. Here they're profoundly unconscious. Here they're recovering consciousness, and here they're awake. And I just want to answer a simple question. I want to take the spectrum in one location, the spectrum in another. I want to take the difference, and I want to get a confidence interval. Just that simple question, all right? Very standard statistical problem, nothing deep about it. Very easy to state, but then setting up a framework where we can do that is what I want to just share a little bit with you. All right? So these are the guys who've done the work. Dimba, who was actually a grad student here and postdoc of mine, and now he's over at Harvard. Michael Baer, who this is actually part of his MN's work that he did. And Seung-Eun Kim, who is now taking a position back in Korea as an assistant professor. So what I'm going to do is I'm going to create a very simple model just building on standard time series things. So just bear with me a bit as I just sort of build this up. So let's imagine that what we have is a time series. So T is going to index time, T from 1 up to capital T. And what I'm going to do is I'm going to assume that this data, or these data, are made up of segments on which the process is locally stationary. So it's here, stationary here, stationary here. Very kind of standard assumption that we use practically. Because what do? I mean, time series theory is built on stationary behavior, and then you move a window along. So I'm just going to assume that I can write that down. I'm just going to make that assumption. And I'm going to assume things are Gaussian here. And we can make it weaker, but I just want to use that. It'll make life simpler. All right? So then what I'm going to do is, if I have a series which is of length t, then I'm going to break it into these k non-overlapping stationary intervals. There's a set of them. And on each interval, I'm going to have j data points. So I've got a whole set of them. All right? So that's the setup. All right? So then the next thing I'm going to do is, so I could write these just as vectors. So this is one such segment. So y is equal to x plus epsilon. Y is those are the data. Oh, thank you. That's this sort of underlying stationary process, locally stationary process on the kth interval, and there's the noise. So I just put down an example. So like we record the EEG data at, we record at 250 hertz. So this would be like 3 seconds worth of data, basically. And this is if you had 2 hours worth of data, you'd have about 2,400 such intervals. All right, so that's the setup. Nothing fancy. So let's just remind ourselves of the basic thing we can always do. So you can take the data. Here's the data on that segment. You taper it. You Fourier transform it. Okay. And then what you get out, and if you taper it specifically with the Slepian tapers, we follow this paradigm that was laid out by David Thompson from Bell Labs back in the 80s. You get the multi-taper spectral estimate. Okay? Because what you're doing is, each taper basically gives you almost an independent time series of data. You Fourier transform that and you average over those. And that averaging, helps minimize this bias variance trade-off we all know about. Okay? So this is that average right here. So this is what that spectrum would look like. So here's what it would look like applied to these data. Okay? So this is the spectra, the eigenspectrogram coming from one of the tapers. There it is from the second one and the third one. You average these together, and you can see you get something that looks sharper. Okay, so that's what the standard off-the-shelf technique would do for you. But if you look up here, you see all this haze up here, up there. It's still up there. And if you look in here, so this is sevoflurane, it seems like there is this sort of third oscillation in here. All right? So now, let's look at a very simple idea to maybe get around that. All right? So let me take this locally stationary quantity, this part of my data, and let me just write it in terms of its spectral representation, right? So it's just the W is just effectively like the inverse Fourier transform. I've written this in discrete form here. So these delta ZKs, which I'm going to assume are Gaussian. These are the orthogonal increments, right? The orthogonal increments plus the noise, and so that's what my data is made up of, right? And so what I'm going to do is I'm just going to assume that I take the increments here, and they're related to the increments here by just a very naive random walk model. Okay? So that couples the information together. So now you can probably see where this is going to go. We've got a state space model, a very simple state space model, where this is the observation, and now I'm coupling the increments together so that delta ZK is like delta ZK minus 1 plus some perturbation. All right? Nothing fancy. All right, now, what the interesting thing happens when you now flip this into the frequency domain. All right? If you flip this into the frequency domain, so what you do is take the data, taper it, flip it into the frequency domain, the model takes on this form. So this is the, let's be concrete. Let's say I have 3 tapers. So this is might be taper 1, the data from taper 1. Okay? And it's been Fourier transformed, so that's what the observation looks like. And now I have the state equation where the W has basically disappeared. It's because when you multiply f, the Fourier transform, by w, they're orthogonal, so you just end up with this equation here in the frequency domain. All right. So there's a really nice result in Brillinger's book that tells us that if we choose the tapers in such a way that they are orthonormal, then this guy here is a realization of this. This is a realization of that, and I have m such realizations. And so I'm kind of back in the same tapering phenomenon. I have something I can now average over. But now I've also added a constraint in time, and I have a constraint across series, so I should get, hopefully I get something good out of it. If not, I had fun doing this, all right? But we'll see, all right? So the way you then compute the updates, you just plug this into a Kalman filter routine. It's very straightforward. There's nothing fancy here. But what's interesting is this. You have m, j one-dimensional complex Kalman filters. So these are what they look like. They're very simple, but they're all parallel. They're all independent because the z's are independent. So this is extremely fast. It just runs across like this. So here's a taper. It has j of these. They run across. Here's another taper. It has j and so forth. And then once you run it one step, you then just average across them. And now you're using time as well as the tapering. All right, so that's the multi-taper idea. So you get this. So there's the Kalman gain. And that's what I just said. That's the average. You just average over those sets of tapers. So that's the state space multi-taper spectrogram. If you didn't taper, you would get a state space periodogram. If you didn't taper at all. And if you just did no tapering or no state space, you'd be just back with a periodogram. All right, so let's just look at how this works. All right, so this is time on this axis, and there's the drug dose being turned up and down. All right, it seems like every time you turn the drug dose up, like right here, right here, right here, right here, you get this third oscillation that seemingly appears, okay? So this is actually me in the operating room doing this. I'm going up, down, up, down. I did it for this talk. No, I'm just kidding. No, stuff like that. So, but you can see going up and down, all right? So there's the periodogram. There's the multi-taper. Now here's the state space periodogram. It's a periodogram, so there's no tapering. And if you put the tapering together with the temporal constraint, it looks like this isn't here, perhaps. And then when you stand back from it and look at it, what's more likely to be occurring is not so much that a new oscillation is coming in. The power in the upper band is seeping down this way. The power in the lower band is seeping up this way. And because you have leakage in these techniques, right, what it's doing is it's making it appear there's a third oscillation when indeed there isn't. So this really matters to us because if it's there, we have to come up and explain why it isn't. So what we think is it may not actually be there. All right? So I'll show you one final example. So this is that increasing doses of propofol. And we did the same thing, use a state space model. So here's the spectrogram I showed you before. Here it is using the state space multi-taper. So one of the things you can see is it's denoised this quite a bit. There's a tremendous amount of denoise. It's about 10 dB in these cases. All right. So if this is a plausible thing to do, you can get a huge reduction in like the background noise. And there's one other thing that comes out of this that you don't get out of standard spectral analysis. You see these red lines here? So I'm showing you the black lines are showing you examples of data taken at these various time points, just to show you how the data in the time domain is changing. The red line is the time domain estimate. All right, so normally in spectral analysis, what you do is you just estimate the magnitude. But because we're estimating the z's, the delta z's, if you inverse Fourier transform, you actually get an estimate back in the time domain. So that's what this is here. So I just want to take these various areas here and now compare them. And this is trivial to do because if you can run a Kalman filter this way, you can run a backward filter this way, so you can get the full joint distribution. So with Monte Carlo, you can just construct the differences. So that's what I just did. So here's what they look like. So this is just seeing at the point of loss of consciousness for like 2 seconds of data, or two seconds of data, what do the spectral differences look like? And so you can see there are areas there where there are large differences, some where they're not. and so forth. So this is just the effort that's necessary to answer a fairly simple question. And what it boils down to is trying to get an estimate of the joint distribution of the data, all right? And I'm taking advantage of the fact that I'm putting a temporal constraint on the data to essentially do that, all right? So what have I just shown you? This state space multi-taper analysis. You can get a formal spectrogram estimate. You can run it backwards in time. We estimated the parameters using EM. Very straightforward way to do that. It builds an empirical Bayes framework. This is that inverse computing getting a time domain extract. You can extract any component. So this actually gives you can have a filter that pulls out any frequencies that you want to by doing it this way. And I showed you could see the enhanced spectral resolution and denoising. All right, so I'll stop there. Thanks.